Hello, this is my final project, the Grid Synchronous Full Bridge Inverter. It takes 48 volt DC from a variable or unknown ripple bus source, and it outputs a clean 29 volt RMS AC output back through the grid, through the UMISH grid box. This is running a full bridge topology, switching gate signals at 12 volts and 10 kilohertz, and it's receiving PWM signals from the TI Launchpad that's connected to the computer using PLECS and PLECS coder. The PLECS coder blocks are taking the control system designed output signals, converting them into PWM signals to the hardware, and the hardware op amp and sensor circuits are sending 0 to 3.3 volt signals for the PLECS coder ADC blocks to read into PLECS and use as feedback to close the loop.
So how difficult was it to use PLECS coder after you got all the simulations working? Is it fairly straightforward?
I think at first it was difficult to figure out how the blocks function with respect to the blocks in PLECS coder or standalone PLECS. Once I was able to figure out the relationship between the signals of PLECS and how the blocks are set up to the discrete blocks of PLECS, then it was pretty intuitive. So long story short, once I got test case PLECS codes of ADCs to read my voltages and really sample or simple open loop PWM signals, then integrating into the closed loop was actually pretty quick and pretty easy. Going back to the hardware, I'm supplying the voltages for my gate signals through desktop power supplies. It's very important for the full bridge inverter that the high side switches have their own isolated power supply, since the switching signal from voltage gate to source, the source is connected to the AC lines, not the reference ground. So those are floating grounds, hence the need for isolated power supplies. I have an oscilloscope over here where the green signal is going to be connected to the AC output of my board, and the blue signal, which I haven't really fully tested yet, but this should just be the output of the full bridge before my LLC filter, which is designed to reduce the harmonics from my switching frequency, 10 kilohertz, and also the high transients from turn on and turn off. And then I also have a fuse to protect the DC side, and then a fuse to protect the AC side. I can't really remember the values. I think this is, it's on the board. 10 amps and then 10 amps.
Nice.
Okay. I'm done pre-charging my, one thing. I did a sub-circuit function for a monitor safety circuit. This is also my presentation. But basically, it's a state machine that's watching the DC bus voltage to prevent inverting operations in unsafe conditions. So my unsafe condition is when the bus voltage is less than minimum voltage, which I think I set at 46 volts, and max voltage of 50 volts. So
Wonderful. Excellent.
perfect. So now I'm going to get started. This is set at 40.
So right now you're just gonna put it into a resistor, right? Or how
No, I'm putting it straight to the AC source. I've already tested the resistor.
You mean the AC source? You mean that thing? Oh,
Yes.
So you're going right into the grid.
Yep.
And you can synchronize.
Yes.
Spectacular.
Yeah. There is one thing. The circuit breaker does come off after like 10, 15 seconds.
Okay.
I think whoever built this box, or what department, they put a sensing circuit to notice if any students are supplying power back to the grid after an X amount of time, shut off.
Okay.
So
Okay.
unfortunately, in my case, my objective is to supply power to the AC, but it was working really nice.
Beautiful.
Okay. Do you mind if I ask you to hold this?
I will hold it for you.
Okay, thank you very much.
Okay.
The circuit breaker is reset to off. I'm going to first set, or I'm going to do this simultaneously because my controller actually does initially for the integrator blocks. You know how there's an initial condition? I did set my initial condition to 60 hertz.
Okay.
But the closed loop control will make sure it continues 60
But
hertz.
you need to start somewhere all the
Yes,
time. Right.
Exactly. Okay, so 48 volts. Oh yeah, one last thing. That monitor circuit, it shows up red LED over here when it's not safe. Once this turns into 48 volts, this red LED will turn blue.
Wonderful. Beautiful. That's very cool. It's very cool you added that. That is just awesome.
Turn. It's not good. And then, oops, I forgot to reset it.
Oop.
Uh-oh.
It's okay.
Oh, it's working. Just
There we go. Oh, look at that synchronization.
yeah.
Yeah,
And that's all good because of the PLL, the phase lock loop.
And this is all a digital one, which you designed in PLECS Coder.
Yes.
Okay.
And the same control I did presented in class.
Spectacular.
Oh, and my name is Shubham Shedge, by the way.
Congratulations. Beautiful
you.
piece of work. Thank you. All right, man. This is spectacular.
Thank you very much.
You learn a lot.